Many people ask me how they can become better hardware design engineers. And many people ask me how they can start with hardware development. And I always tell them work on your own projects. In this video, we are going to talk to Sam, and he is going to share how he went from an idea to working prototype. So I really hope this video is going to help you to get an idea what are the steps in this development process. What are the steps when you would like to design something from your own idea to a working prototype? And I really hope this video will inspire you and will show you that it is possible and it is actually not so difficult to create something what you always wanted. In this video, I'm going to play a call which I had with Sam. The call which I recorded and where Sam is talking about his latest open source project, which is called Magic Wand. And basically, the project is about creating a wand which can be used to control, switch on and switch off different electronic devices. Maybe you remember I have already created a video with Sam where he was talking about how he designed these open source smartwatches. And you may also know Sam from his different project which is called Smart Glasses. All the Sam's projects are open source, and if you would like to have a closer look, just go on Sam's GitHub. Here you can see all the files for the smartwatches. So here are the PCB files, schematic, software files. Here you can also find all the files for the smart glasses. And also for the project, what we are going to talk about, the Magic Wand. This project, what Sam is going to talk about in this video, is basically a wand with battery powered circuit, and this circuit can sense the movement of this wand, and through Bluetooth it can send these movements to a plug which can then switch on or switch off the devices which are connected into this plug. Okay, that's everything for introduction. I really hope you will find this video interesting and you will learn something new. Sam is going to start with answering the question, what kind of project you may want to work on. So here is my recorded call with Sam.
Do projects that excite you. Do projects that are kind of either they solve a small problem for you, or if there's something that excites you, maybe that's the thing to do, right? I've had friends that have kind of said this. They've asked me the same questions. What should I make? The first thing you should always make is the thing that you're gonna finish, right? It's the project that you get so excited about you want to finish it, because that's where you learn the most. So I can't tell you exactly what to make, but I can tell you that making something that excites you will be the best learning experience.
Actually, my next question is about what keeps you going, because some of your projects, I think the smartwatch, it was like over half a year, even maybe almost a year, no? Or
No, it wasn't that long. But I understand the issue. To be completely honest with you, the issue that what the answer for me is I try and get it done before I get bored. Um,
but
it's
it
really
takes
there's
a
like
long
there's like
time to get bored.
right. Yeah, I mean, I think probably for me, um, my internal timer is probably about, if something is going to take more than 3 months, I'm probably not going to finish it. So I think that the watch was right on the edge. It was about 3 months to do the whole thing. The glasses were actually pretty quick. The glasses were about a month, and the wand was about a month and a half. So I mean, that to me is that's the best way for me to avoid, getting bored of a project and moving on. Is I try and pick things that I can do in a relatively speedy amount of time.
So let's move to be more specific. Let's
Yeah,
talk about this project.
let's do
And
it
so, how did you start?
for this project.
Yeah, what was the first thing? What do you normally do? You come up with the idea, and then what is the next step? I have some, but I would like to know what are your next steps.
Yeah, I think it differs per project. Sometimes I start with the kind of the housing or the mechanicals. Like sometimes I start with like how I want it to look. Right, that's the most important part, and then I try and cram everything else into it. Um, and sometimes it's the other way. Sometimes how it looks isn't that important, so it's about getting the electronics and the code and everything right.
So let's be specific
Um,
about this wand.
yeah. So specifically about this wand, I think I actually took the route of how it looks is the most important thing, right? Because the whole point of the project for me was I wanted a magic wand that looked like I went to, like the Harry Potter store, and I was going to Hogwarts for school next year, and I needed to buy a magic wand. So that was the most important thing, is I wanted to find a way to fit all this technology into this form factor, this shape. Um, so I started out with kind of putting together just roughly, what I thought a wand should look like, right? And I'm scrolling through Google images of what do different magic wands look like and things like that, and I started putting together kind of some ideas of what I liked. And so then after that, as I kind of came to a shape that I liked, but the most important part of it was when I hold it, it has to be a certain diameter, a certain width, right? Like if it's too big, if I'm trying to pack a lot of stuff into it, if it's too big, it doesn't really feel like it doesn't feel magical. It doesn't feel like a magic wand. It feels like I made a big piece of technology and I made it look like a wand. Um, so with that in mind, that was kind of the biggest priority. Where it's like trying to figure out a way to cram all this stuff in, and make it look nice. After I went through that, the next step was I actually I took kind of a weird route for this one. I actually started developing firmware before I started doing the schematic and the layout.
So you still had the wand in your head, or you also did some 3D
I did some
drawings? Or
3D modeling, and actually, let me see if I can. I might have a bajillion different layers of this, but I think this was actually the very first. Let's see if this will open up.
so basically, you started like Magic Wand and Google Images, and
Yeah. So here you can see this is kind of like, I wish I was good at drawing. I feel like that would make my life a lot easier. I'm not good at it. So typically, like to put ideas on paper, I'll go and I'll like open up some 3D, some CAD, and I'll start creating shapes, right? So I was like, okay, this was kind of the shape that I thought I wanted, right? And I started thinking through, okay, maybe there, like, how can I make this, right? I was like, okay, well, I'll make a top part, a bottom part. Maybe I'll buy like a dowel from like a hardware store, and I can use that as the wand part. And I have to find a way to hide stuff. So I started thinking through all that, right? And then as I started thinking through it more and more, you can kind of see here a whole bunch of different parts on the side. As I started thinking through it more and more, I started getting a little bit more intricate with my designs, which ultimately led to this. And we can talk about all the different parts individually, if you'd like, and kind of how they all fit together.
but initially you only had like this shape and maybe idea. Okay, it's going to
Yeah.
fit, but you didn't have all the parts.
No, no, no. Yeah. So originally it was, if you imagine it was just one solid piece,
Yeah.
that I was thinking was going to be this shape, and I knew it had to be no wider than this, this width. Maybe
Did
if
you try
it's
to build it?
No, I didn't, because the I guess for me the most important part, right, was when I was holding it, I wanted it to feel like a magic wand. So I went around the house and I just started picking up things that were kind of, long and narrow. So like if I held up a pen, does this feel like the right size? No, it's a little too small. What about like a Sharpie? Does this feel the right? Oh, this is closer. I started picking up different things just around the house. So say, is this too big? Is this too small? Type of thing. And I think I narrowed in. I want to say it was maybe 16 millimeter. It was the width that I felt for my hand
Mm-hmm.
was the right size. And I'm sure it's different for different people. But for me, that was the right size. It felt like this is something that I could keep in my my wizard robe, and I could pull it out, and it would feel like my magic wand.
So you knew how it is going to look, and
Mm-hmm.
then you took some reference board, I think, and you
Yes.
okay. Let's
Yeah,
move
I
to
have some. I
this.
have some development boards, and I actually have one right here, so I can show you. I have these development boards that I bought, and right, it has the Bluetooth micro that I wanted to use, and I soldered on a little accelerometer development kit as well, and this way I could play around with it a little bit. But the most important thing was I needed to make sure that I could write some firmware that would sort of work. Um, and again, I do hardware for a living. I do schematic and PCB layout and type stuff. So if I can get the firmware working on a development board, I feel very confident that I can get the hardware to work. Um, so after I did the 3D modeling, the next step actually was doing the firmware kind of on these development boards, and I have two of them. They're both just development boards for the Dialog semiconductors chip, um, and they work great. Right? I mean, they serve their purpose of just being
What did you
developed.
use? Can we show some, so people get idea what they can use if they would like to start with Bluetooth?
Yeah, I can find it. Uh, DA 14531. Let's see. So if you go here, I believe it's this one right here, the DA 14531 USB development kit.
So did you buy two of them?
Yep, I bought two of them, and one was going to be one is the
Receiver or
smart plug, yeah, and
okay.
one is the wand, right? So I have two of them, and really when I started out, before I even soldered the accelerometer on, they just have a little user button. So I was just, can I press this button and turn a light on this one? Great. And if I could do that much, I felt that I could make other things happen. Um,
So what everything you had to do to make this work?
on the firmware side,
Yes.
okay. So this was actually the trickiest part of the project was the firmware. And it wasn't so much that the actual physical code writing was hard, it was the architecture of the project, right? So normally when you have a Bluetooth device, typically what happens is you turn on your device and it comes to life as a Bluetooth peripheral. And so in Bluetooth, there are kind of two basic kind of roles that a device can take. It can be a central or a peripheral. And I'm kind of doing some hand waving to simplify it a little bit, but that's the most common. You're either central or you're a peripheral. And if you're a central, typically what you're doing is you are the device that is looking for peripherals, and you're the one that's connecting to everything. And the peripheral is the device that is, maybe it's your headphones, or maybe it's your watch or something. It's the device that is kind of being interacted with, right? And so normally when you do this, the way it works is you turn on the peripheral, and the peripheral starts shouting out into the world. It goes, hey, I'm here. My name is Bluetooth peripheral, and these are the things that I can do. And so this is called this is the advertisement packet that the device sends out. So it says, my name is Bluetooth device, and you can check accelerometer data with me, or you can look at my battery level, whatever it may be. And then the central device will say, okay, I see that, and I'm looking for that. I'm going to connect to it. And once I connect to it, we can kind of exchange some data. And that's the typical Bluetooth path. I didn't want to do that for this project because I wanted you to be able to wave your wand around, and I wanted you to, if you wanted, turn on one light, two lights, all the lights in your house, or maybe all the lights in your house, the blender, and your sprinkler system, right? I didn't want you to be limited to connecting to one device at a time. I wanted it to be everything. So I kind of switched the roles. The wand, instead of being the central device looking for individual smart plugs, is actually the peripheral. And the individual smart plugs are all the centrals. So what's happening now is the wand, when I wave it around, it turns on, or it comes out of like a sleep mode. And it goes, hey, I'm a wand. These are the things that you can do with me, in its advertisement packet. But you can't connect to it. It doesn't allow anyone to connect to it. All it's doing is when you wave the wand around, it changes its advertisement packet. So it says, hey, I'm a wand, and I was just swung to the left. Hey, I'm a wand. I was just swung left and then up. And that's all it's doing. And so then the plugs all around you are constantly scanning all of the devices. And if they ever see a device with the right gesture, the right spell, right, then they can turn on or off. It may not sound that complicated, right? But at the time, kind of thinking through it and thinking through the problem, that was definitely the most challenging part. And that was the one that, like, I'd go to bed, and while I'm lying in bed, I'm thinking about it for 4 hours before I can actually fall asleep, type of a thing. I'm like, how am I actually going to do this?
That's why I always sleep with my TV turned on, so I can't think.
You can't, yeah.
But then
that's so smart.
But then I wake up, and when I jump from my bed, I go to my computer and write down all the ideas what I had in the night.
Yeah, it's gotten bad. It's gotten to a point where sleeping has started getting, the amount of time I sleep is smaller and smaller now, because I'm always like, oh well, maybe if I do that. Yeah, so the architecture was wrapped up, and once I had this kind of idea of how I wanted to do this, then it was just a matter of, okay, I need to take this one development board, and I need to make sure that I can change the advertisement data on the fly, right? So that when it comes out of low power mode, I can actually change this advertisement data. And luckily, again, I'm not a firmware person, so all this firmware stuff is I can do it, but I'm not amazing at it. Luckily, Dialog has some really great
Is it somewhere on the website?
Yeah, let's see if we can find it really quick. They have a whole like software development kit, a whole SDK. Let's see. I'll just go back to the actual chip. So they have a whole SDK with a whole bunch of example projects. They have a ton of, let's see if I can. They have a whole bunch of example projects that you can play around with, right? So
how does it work? Like you can. There is software for Windows and software for Mac, and then you can upload firmware, or how does it work?
So all these example projects are just like a combination of .c files and .h files, right? Header files and .c files.
And what do you do with these C files?
Yeah, they recommend using the Kyle IDE to run everything, and they have a whole bunch of documentation on how to like actually get started and run these example codes and everything. So let's see if I open one up.
So you need to buy a JTAG and then load the firmware which you compile with Kale. You load it through JTAG to the board, or you can use the USB.
On the development boards, you don't need JTAG. Yeah, you can just use you can use the USB. On my boards, I have a JTAG for. But yeah, these boards come. They come with full. Everything is integrated all the way through. So, you hit flash and everything just loads.
And how do you debug then the firmware? Like through USB, you can read like serial communication, and you can see something has connected to your device, or how does it work?
Yeah. So through the USB plug, you have access to both serial data from your device, as well as you can full like debug, put breakpoints in your code. So if you want, if you don't have to do anything through serial, but if you want, you could, put a breakpoint at this line of code and see what this variable looks like when it hits this breakpoint, which is very helpful. Especially when,
So it's like
when you're
building
doing,
JTAG?
Yeah.
Okay.
Yeah.
And you can debug it directly in Kale?
Mm-hmm.
Okay, perfect. Oh, that's
Yeah.
good.
Yeah, it's great. And so here's like a good example, right? Like this is for their BLE Eddystone beacon with hibernation or deep sleep. But you click on this example, you can download it. So the example can be downloaded from here. You would click on this, it would be a zip file with all the different files in it. But then they walk you through everything. This is what you have to plug in. This is how you run the setup. Start Kyle, open this, blah, 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 blah. And they talk you through everything, which is really nice. And it makes it very easy for someone who's firmware dumb like me to understand this stuff and actually make it happen.
And how difficult it is for people to understand Bluetooth protocol from this documentation? Do they need to like study it a little bit differently? Because I know I've done I was curious, so I created one project on Bluetooth, and I know it's not only about the communication and the firmware, but you also need to understand what these devices are talking about. So you need to some kind of get background about how Bluetooth works.
I would say that if you are just starting out, there are some good websites that have just like a quick intro to BLE, explaining the gap, the GAT, the services, characteristics, descriptors, all those different things. Like there are a ton of things that go into it, and it can be overwhelming and complicated. The way I like to think about Bluetooth, and you can cut this from the video if you want. The way I like to think about Bluetooth is I think about it like a big apartment building, where the device that you're communicating with is this apartment building. And so when you walk into the apartment building, you go inside, and the way that the information is structured is each floor is a different service. So I can go to the second floor, and that's this particular service. And when I walk onto that floor, then I have to go to the right apartment building. And when I go to the right, apartment unit. And when I walk into that apartment unit, I can talk to, a person in that unit, and they give me a certain amount of information. Maybe going to the sixth floor, and I'm doing just heart rate like maybe the sixth floor is dedicated to the heart rate services. So I walk down this hallway, and I'd have to actually look up and see what the protocol requires. But like, say, I'm walking down the hallway and say, apartment B is going to give me just beats per minute. So I walk into apartment B, and they say, hey, 70 beats per minute. And I say, thank you, apartment B. And then I walk across the hallway to apartment D, and they say, hey, the oxygen level in your blood is at 95%. And I say, thanks, apartment D. And then I walk out, and then what I can keep doing is I can just keep going back and forth between these different apartment buildings on the heart rate floor, right? And I'm just collecting this information. Then I can do with that information whatever I want. But that's how it's organized. And then maybe instead of going from floor 6 where it's doing heart rate stuff, I actually want to know how much battery is left. So I'll go down to floor 5, and I'll walk down to apartment C on floor 5, and I say, hey, how's your battery doing? They say, we're doing great. We're still at 48% battery. And so that's kind of how it's organized, right? It's almost like a big structure. It's a database, but it's like a big apartment building. And so you go to different apartment buildings to figure out what information you want. And each floor is kind of like a different department of that.
I have a question.
Yeah.
Because I know when I was doing the Bluetooth, for me, the simplest way to communicate was to use the serial communication service. So I was not really using this protocol. And especially because if you would like to do some customized stuff,
yes,
it's easy just send serial messages. So how did you implement your custom movements?
Yes. So it's a little, the answer is a little bit complicated because
maybe it's very specific, but I'm just curious because there is probably no protocol for magic wand, or service.
No. There is not. Um, but remember, the kind of different thing about this project was I'm actually nothing's connecting to the wand, right? The wand is just advertising what is going on. So
Ah,
when we talk about this apartment building, the apartment building is once you've connected, this is the information that I can find out about you. In my project, in the wand project, there was no specific service because you couldn't connect to it. So when the wand boots up, maybe if you think about this apartment building, the advertising packet is what's on the big sign outside the building, right? It says, come to, Sam's Super Magical Emporium, right? And that's what it says on the big sign. And so you say, oh, I actually want to go into that building. And normally, if the device was connectable, you could go into the building and you could explore all the different floors and things like that. All I'm doing for this project is the sign on the front of the building. I'm changing the letters every time you do something with the wand. So instead of saying, come to Sam's Magical Emporium, it says, come to Sam's Magical Emporium. Also, we're moving to the left. And so by doing that, then the plug, who's in this, crazy analogy, the person walking down the street seeing the sign says, oh, look, the sign says they're moving to the left. And that's all the information they need.
so you
So,
basically build in the information into the advertisement packet.
yeah,
So you are
yeah,
not really connecting anything with anything. They just
correct.
read the kind of information about the wand.
Exactly. Um,
Ah,
that's for this project, right? For other projects, there have been, custom, GAT services and things like that. Like for the glasses that I did in the fall, there was a custom service dedicated to turning turning on and off different LEDs,
so you design your
depending
own
on
protocol basically, or you
kind
can
of
design custom. I didn't know you
yeah
can design custom
it's
service.
it's a custom service. And I'm gonna look this up really quick, because I don't want to tell you the wrong thing. um, let's take a quick look. So when you have like a GAT, right, which is the big database, you have custom, yeah. So the GAT profile in this scenario is like the big apartment building, and the service is just whatever you want it to be. There's a whole bunch of, let's see here, Bluetooth. The Bluetooth SIG has a dedicated list of, if I can find it. I'll find it later and I can send it to you. But basically, there's a dedicated list of a couple different services that are consistent, right? They have to follow a specific protocol. If you want to do something outside of that specific service, you would just create a custom service, with your own characteristics and descriptors and stuff inside. And again, I, I like to give props to Dialogue when I can, because I use their stuff a lot and I like it. Um, but they've done a good job of making it very easy to just create a custom service with custom characteristics and descriptors. And there are a whole bunch of example projects where you can kind of look and see how they're doing it and implement it your own, in your own project type of a thing.
Okay, so let's move a little bit further. So
Yeah.
you had the development kits.
Mm-hmm.
You did some firmware, and I've seen in your video basically everything what you did. You just light up the LED.
Yeah. Yep. That's basically all it is. So but remember the let's see. I have one of the smart plug boards here that hasn't been put in the casework. So this is the board for the smart plug, and obviously it's missing the plug, it's missing kind of the power supply and the relay that turns stuff on and off. But the the IO, or the pin, that the net that runs to the relay in this scenario is the same net that would run to the LED on the development board. Right? So if I can turn that LED on, hardware wise or software wise, it's the same thing, whether it's a relay or whether it's a light. Hardware wise, it just means that I have to implement it slightly differently, but it's not a huge difference. So if I can get the light to turn on, I can get the relay to turn on, and that's what it came down to: is can I wave something around over here and turn a light on over here? And when it worked, it was great.
Okay, so you proved basically that you can build it,
Yes.
and then the next phase was building it.
Next phase was building the electronics. Yeah.
Yeah.
And I'll jump over to the schematics and stuff right now. This main page that we're looking at right now is, if you think of just like a block diagram drawing of everything, right? So you see there's a microcontroller page, an actuators page, power page, and a sensors page. Nothing crazy going on here other than this is just generally at almost like a table of contents. Like you're seeing how the whole thing is going to be laid out. And so typically what I start with is the brain. I start with which I consider the microcontroller. This block here in the middle, the one that's labeled BLE, is that dialogue chip that we were just talking about, that DA14531. I really like this chip.
This one has built in the Bluetooth.
Yes, it's an ARM M0 Plus core, and it has the Bluetooth radio and some additional stuff built into it.
And you can get the kind of firmware where everything is running, and you just build on top of this your own application.
Yeah, absolutely. Which is great. One of the things that I really like about this part, and the reason that I've actually used it now in 2 or 3 projects, this one part, it's really small, it's really cheap, and it uses really, really small amounts of power.
Mm-hmm.
The transmit power for this device, like when it's actually transmitting everything over Bluetooth in full blast and everything's running, I think it's like 4 milliamp or like 3 or 4 milliamp. I know that's the reaction that I had. It's so small.
It's like LED.
Yeah, it's less than, I think it's actually less than the LED that I have on here, right? And not only that, it's 2 millimeter by 3 millimeter. It's tiny. I don't even know if you can see it in here, but the little black chip right there next to my finger, that's it. That's the whole thing, right? So it's really small. It's like 50 cents in high quantity, and it uses super low amounts of power. The biggest downside, and it's kind of up to each individual person, but there aren't that many I/O, right? This is the entire part. I think it's like 24 pins or something like that total. So it's small. There aren't that many I/O, but if all you need is maybe an I2C bus, 2 or 3 I/O pins, and that's it. That's more than enough, right? Like for this project, I needed an interrupt I/O, one I/O to trip the vibration motor, some I2C pins.
For
that was
sensor,
it,
I guess.
Yeah. For the glasses, I had I wanted to make sure that I had different color LEDs, right? So I needed different I/O for each color of the LED. I just put a small I/O expander on this I2C bus. So, right, I mean, like it all kind of just depends on what you need. But like if you need something that is, I just need to turn something on or turn something off, and it doesn't have to happen really fast or whatever it may be, maybe an I/O expander is all you need, and then you can use something like this where you don't have a ton of pins. Other than that, the output of the antenna is 50 ohm. Normally, I would include a little pi network just between the chip and the antenna to make sure that I can tune that impedance. But I don't have a network analyzer here at home because I haven't paid $40,000 for one. And the trace, when we get there, I'll show you the trace length going from the actual microcontroller to the antenna is like 20 mil long. So I was like, I don't have enough space for a pi network, and 2, I'm not super concerned about impedance mismatches right here, as long as I roughly get my my coplanar waveguide math right, type of thing. Other than that, on this page, there isn't much more. I have a little bit of flash memory and a.
How do you use the flash memory?
So it's SPI flash.
But is it it's the firmware inside of the flash memory, or you have it just for some additional data?
Both. Both.
Oh,
The
so there is
when you
no flash inside of the
there's
microcontroller.
no yes, that's correct. That is a downside to this part, right? There's no built-in flash to this part. Um, the way that this part works is it will look for when it first comes on, the bootloader will look to see if there's any SPI flash connected, and then it will look at a specific address for the code.
Mm-hmm.
Once it finds the once it finds the code that it's going to run, it will pull all of that and load it into some internal RAM so that it can run the application code.
So does it mean
This
you have to program this flash before you solder it down, or there?
No, you do not.
Okay, so there
Um,
is something inside of the
there is yeah, there
microcontroller,
is
bootloader
there
or
is some
something.
yeah, there is some ROM, and actually, if you really want to, you can. There's enough memory on here that you could do a one-time programmable flash to ROM. So on the development kit,
Yeah.
they actually have. So let's see. So down here, this is the microcontroller. This black. This is actually some flash memory that they have on the
Mm-hmm.
chip as well. This right
Ah.
here is an Atmel chip that they're actually using to do USB to JTAG.
Ah.
So
Okay.
in between this side of the board and this side of the board, they're two separate
So it's
systems.
like Arduino, where
Yeah,
you have,
exactly.
yeah.
Exactly. So JTAG and everything associated with it, actual micro, right?
Okay.
So I'm replacing all of this with a connector that I'm just plugging,
To
like a
JTAG.
Sega or like a
Yeah.
J-Link into, right? So next up is this is the sensor page, and I because of the global silicon shortage, I actually had trouble finding parts, right? And I'm sure you've seen this too, and I'm sure a lot of the people that are watching this have seen this too. There's just a shortage of parts that I want to use.
Feel.
And
Yeah.
the part that I wanted to use for this particular wand, I wanted to use an IMU. So it's a gyroscope and an accelerometer baked into one. And there's one ST, electronics IMU that I really like that I wanted to use. And I could not find it anywhere. Zero stock everywhere. Um, and so I was digging through, piles of old parts that I have from other projects. And I was like, okay, well, I have, an amount of these LIS 3DH accelerometers. So I'm just going to use this. So that's why there's an accelerometer here and not an IMU. And I want to present that information because if I was going to design this again in a non-silicon shortage world, I would have designed it with an IMU because when you're doing movements and gestures and things like that, knowing both acceleration and velocity is super helpful. Knowing not just the, I guess knowing not just whether I'm speeding up or slowing down in one direction, but knowing if I'm moving at a constant velocity or if I'm not moving at all is very helpful, right? So if you think about it from the point of view of like, um, maybe I'm holding the wand right in this one orientation, and I just turn my hand, right? I rotate my hand. All of a sudden, the wand is seeing a constant acceleration due to gravity in this one direction, and if I rotate it a different way, it's seeing it in a different direction.
But you
The
didn't
wand
move it.
the wand doesn't
Yeah.
know that where that acceleration is coming from. It just knows that there is some acceleration. If I were to have the additional gyroscope, if I was to have the velocity numbers as well, I could show, oh, I'm seeing a constant acceleration, but there's no velocity. So I know I'm standing still and this is just pointing towards the ground, right? So if I was going to do it again and in a different world, that's how I'd want to do it. In this scenario, I had to do a little bit of kind of like firmware trickery and some filtering and stuff like that to try and get rid of some and try and figure out what is actually happening without knowing what the velocity was. So this page is pretty straightforward. It's just the accelerometer. It's read over I squared C, and there's an interrupt because the way that the device works is it goes into a low power mode 3 seconds after the last movement. So in other words, after I do my gesture, if I hold still for 3 seconds, everything shuts down. The device goes into this low power mode. I think it draws like 150 microamp or something in sleep mode. So, my one lipo battery in theory could last like 50 to 75 days or something like that, depending on how much I'm using it. So, and then what happens is as soon as I take the wand and I lift it into a particular position where I'm pointing the wand straight up, that interrupt pin will then toggle and wake up the microcontroller, and then everything starts. So when that interrupt pin wakes up the microcontroller and starts, the microcontroller then turns on this vibration motor for 1 second.
So this is feedback for you that you can make the gesture.
Exactly.
Yeah?
That's exactly it. So because it looks like a wand and there's nothing else there to indicate it's listening, it's time to do stuff, I thought, what's a cool magical way to know that you're ready to cast your spell? Well, the wand has to vibrate with all of this magical energy, right? So you lift your wand up, it vibrates in your hand, and as soon as it's done vibrating, that means, okay, it's ready to start listening to gestures. So on this actuator page, there's literally one thing. It's just this tiny vibration motor with a little FET to turn it on and off and a flyback diode. And that's it. Nothing too crazy, nothing too special. To run everything is here on this power page. Right. So this is, we talked about earlier, this is like that digestive system. This is like what's going to take the energy in, what's going to turn it into usable energy for the system, and then what's going to distribute that energy, right? So the charger and the battery are pretty self-explanatory, right? The battery it's a lithium polymer battery, and the charger is just there to charge that battery. This stuff is the more interesting stuff, the top stuff, the protection and the buck. The buck is the regulator that we talked about earlier, right? This is going from that battery voltage to 3.3 volts.
How effective it is?
What's that?
How effective it is? What is the efficiency?
I'd have to go and look at it. I want to say it was like 85 or 90%. It's pretty good. It's not perfect. Nothing is, but it was good enough. It's tiny. It's this little like 5-ball BGA. Which is one of the reasons I'm using it. Let's see if I can show you.
Because it's very small, yeah.
It's so small. So let's see if I can point it out to you guys. So the little black dot right there next to that big inductor and that small 0402.
The inductor is bigger than the chip.
The inductor is bigger than the buck, right? So that guy right there is the little buck. It's tiny. It does a good enough job. I've used that part before, so I knew it would work the way that I wanted it to work. I was happy with it. That was that. And all it requires is some input capacitance, some output capacitance. There's no feedback pin to for like an adjustable voltage or anything like that. So again, I'm just trying to think about minimizing part count to keep it all in this small space.
I only ask because I was working on a project, a battery powered project, and we had to count like every microamp, and I was curious, like,
factor.
Yeah.
For this project, it wasn't as much of a factor because let's see if I have one here.
It sleeps all the time.
It sleeps all the time. The power consumption of the device when it's fully active and going crazy is 5 milliamp or something like that, and that's like when everything is on. And these are the batteries that I'm using. They're 10440, so 10 millimeters by 44 millimeters is what they're called, but they're basically just AAA size lipos. And each they say they're rated for like 350 milliamp hour. They're probably 250 milliamp hour, something like that. But, again, when I'm using 5 milliamp active for 10 seconds every 2 hours, 3 hours, and then it's sleeping the rest, it's such an insignificant amount of power draw compared to the size of that
Yeah.
battery that I wasn't super concerned with the efficiency. It is a big deal in other scenarios, right? Like the glasses. I don't have one of the boards around me, but the glasses I was using a tiny lithium ion coin cell battery, and that, I mean, those, I want to say it had like 10 milliamp hours or something. You know, it was tiny. So for that one, it was a really big deal to figure out the efficiencies and make sure everything was good. Other than that, on this page, there's this protection circuitry.
Is
and so
this
all
the
that,
same one as in your smartwatch?
I think it is actually. Yeah, it probably is. So very similar design, very similar idea. All it's doing is it's disconnecting the grounds between the circuit ground and the battery ground when the battery is in a is in a state where it needs to be protected, essentially. So if the voltage is too low, where you might damage the cell, or in, I guess the flip side is true as well. Like if you were to accidentally apply too high of a voltage, you know, an over voltage scenario, it would just disconnect the battery, so that you don't accidentally damage the cell. Excuse me. That is the schematic. That's the whole thing. That's the entirety of the wand. What makes sense to do now? Do you want me to jump into layout? Do you want to talk about?
Let's have a look also on. I'm thinking what would be better.
Yeah.
Layout. Okay, let's do layout.
Yeah.
And then we can do the socket.
Yeah. Yeah, for sure. All right. So pull up the 3D view first. So this is the layout. This is the whole circuit, and
nice 3D model again.
Thank you. So here, I can't remember the exact size of the board, but we'll do a quick measure. So the board is, so there you go. The board is 10.5 millimeter by 30 millimeter. So it's a very, very small board. And actually, I made sure to pull one out before we, so let's just hold up. So this is a AAA battery, right? AAA battery, and this is the one board. So you can get a feel for how big everything is and how much space I actually had. Not a lot. I wanted to keep all the assembly on the top layer because I'm assembling everything by hand, and I didn't really want to do a double-sided assembly. I've done them before, but if I didn't have to, I'd prefer not to. So yeah, so
everything is on one side. All the components are on one side.
All the components are on one side. Yeah. So this is the back side. The only thing on the back side is the JTAG. So flash it on the back side, and then this is the front with all the components. We'll quickly just like run through like what the placement of everything is, and then if there are sections that you want to talk about, maybe we can jump into those to give you a better feel. So you may notice these castellated pads in the corners. So we'll talk about it a little bit more when we get over to the 3D model. But this castellated pad here on the right-hand side is the positive terminal of the battery.
Mm-hmm.
This is the negative terminal of the battery. These two castellated pads are for the charging contacts. So this top one is ground. This bottom one is 5 volt. Other than that, let's see. So down here, can you see my mouse?
Yes, I can see.
Is that coming through? Okay. So the stuff here in this bottom left corner, this is the protection circuitry stuff. So this is that little protection IC. This is that dual NFET package. This guy right here is that little buck converter that we were talking about. This is the inductor for that buck converter. This right here is the battery charging IC. This right here is the flash for the device. This is the micro. You can see that little tiny trace going straight to the antenna. This is just the crystal for the micro.
Is it like ceramic antenna?
Yeah. It's a small, it's a Johansson ceramic surface mount antenna. Let's see if I can show you see if you see it. Can you see it right there? The little white.
I can see it.
Yeah. So that's the antenna for this one.
And then you
And we'll talk
remove
about,
the copper?
yeah, so there's no copper directly below it. And we'll talk about why I hate the placement, but it was kind of the best I could do for this scenario. One other kind of weird thing about this microcontroller is typically for a micro, you have an active low reset line. So if in order to reset the device, you pull the reset line from high to low, and that resets it. For these dialogue chips, it's the inverse. It's active high. So in order to deal with like the way that a lot of tool chains do the reset pin and like, you know, when you're doing the JTAG stuff, there's a little PFET here that just inverts the reset line
Mm-hmm.
so that it's seeing the right thing. And I don't have to tweak any of the tool chain stuff to change that. Otherwise, up here, this is the accelerometer, that LIS 3DH. And then all of this stuff is related to the vibration motor,
Mm-hmm.
which is right here. All right, so this is the little FET, flyback diode, current limiting resistor type of stuff for that motor. That is the whole thing, right? That is the entirety of this design.
And is it enough that you basically hold the, or where exactly it is placed in the wand?
It's right under your hand. So there's a lot of the Bluetooth radiated energy is attenuated by your hand, which is not great. I agree. For the signal integrity, right? Like
Yeah.
it's not going to hurt you, but yeah, I mean, it is just one of the unfortunate things. That being said, I'm still getting pretty decent range from it. I mean, my house is not huge, but I can be, you know, on one side of the house and wave the wand around, and I can turn stuff on the other side of the house. You were asking about the copper under the antenna. You can see here, all this is removed right here. The board is actually, it's a 4-layer board. So the red is the top layer. The blue is like a ground plane on the second layer. This yellowish color is the 3.3 volt rail power plane. And then the bottom is just more signal with another kind of ground pore around it.
Where do you manufacture your PCB?
So all these were made by PCBWay in Shenzhen.
Yeah.
Right. But they've done a great job. I would say that probably been using them for personal projects for 5 years, maybe 6 years at this point. And I don't want to like turn into an advertisement, but like I've consistently had really good.
I know them.
Yeah.
Yeah. We have been providing some coupons our students
Okay,
for
good.
some
Yeah.
time from
Yeah,
this.
I really like them. I've had really good experiences with them. Even their customer service, like if I have questions, they get back to me pretty quick. Price is good. The speed is really good on them. Like, you know, the boards that I had made, these are the smart plug boards. I don't know. I probably ordered them on like a Thursday, and the next Tuesday or Wednesday they were at my house. You know, and they were, I want to say I probably paid $50 with shipping for maybe 50 of them or something. I mean, the crazy thing is that if I had these capabilities when I was in university, back when I was in college, I mean, to think of the things that I would have done, right? You know, it's great now. I'm so excited about it. I'm so excited that this exists. But younger me is very jealous of older me having the ability to do this kind of stuff.
I agree. I completely agree. It's like when I was younger, I had to everything do myself, and it
Yeah.
was so bad. We only could make like 1-layer PCB at home,
Yeah.
and it was like maybe I had to do it 5 times to make it right, and it was still ugly and bad.
Yep, that sounds about right. When I was in college, we had like our senior capstone, like our last big project that we needed to graduate, and I had a team member, and this team member he designed a PCB, which was not something that we did in college. So this was like he like went above and beyond, and we put together basically all of the money that we had for this whole project went to having one board made. It was like it's like $400 to have one board. You know, it was yay big. It was a 2-layer board, and I think it took a month to get to us or something like that. You know, for them to make it. And so it's just, you know, it's stuff like that. You know, to think, you know, $400 for one board, you know, versus I can pay $20 now for 100 boards. You know, it's just the order of
Exactly.
magnitude of things is great.
Do they have
Uh,
a stack up on the website with impedances?
you do, yeah. So you can go on their website. They have they show you all their standard stack ups for their different layer counts and different widths, right? So this WAN board, I think the WAN board and the smart plug board actually are 0.8 millimeter thick boards. They're not the normal 1.6 millimeter.
Okay.
And part of that was because with these smaller thickness boards, the way the stack up worked out, the antenna trace could be a pretty normal size trace. I think this ended up being, let's see, what is this? This is 0.2 millimeter width.
Mm-hmm.
You know, the bigger the gap between this top layer and that reference plane, the bigger that width has to get. So I you know, one for size reasons, but two because it makes that antenna routing a little bit easier. I've been really liking the 0.8 millimeter stack ups recently. But yeah, they have a big, you know, big page dedicated to, you know, if you want a 6-layer board at 0.8 millimeter, you know, thickness, this is what the stack up looks like. This is what the dielectric constants are of all their different prepregs and their cores and everything like that.
Do
So,
they suggest also the impedances and or do they have calculator for impedances, or you have to use like Saturn PCB to key
I
them?
use the Saturn. Yeah, in fact, I have it right here. The Saturn PCB tool. Yeah, I don't remember if they have dedicated. I don't think they have like dedicated numbers for like use this trace width and this, you know, this spacing.
This is
They
actually
just
why I use JLC PCB, because they have also
they,
calculator.
oh, that's nice. That's really convenient. I've actually been thinking about trying them out. One of my coworkers really likes them, and I've been thinking about trying them out because I want to try out their assembly services. I know it's limited to like their select library, but I have a couple of projects in mind where, you know, I just want like a couple of boards with some LEDs that I might be able to connect up and stuff. And so I think I'm gonna give them a go at some point in the coming weeks or months.
I've seen some videos from Philip. You probably don't know him, but he's using KiCad and he's using JLC PCB, and he also always builds the PCBs directly in JLC PCB. And I was surprised. Like, price is very low, and you
Yeah.
don't need to handle components. You don't need to solder it. They do it.
Right. Yeah. So that's the big thing that I want to try is their assembly services are really cheap for us for their library of
Yeah,
parts. Right.
exactly. Yeah, you need to
If you're willing
use
to use
components from their library. Yeah.
right, if you're willing to use their parts, it can be pretty cheap. So I definitely want to give it a go.
Okay, so
Yeah.
basically, when you buy this PCB, you also get the stencil. I guess I think.
So you can through PCBWay. I actually use a company called Osh Stencil.
Ah.
Um, I started using them before PCBWay started offering the PCB or before they started offering stencils. And Osh Stencil has been again consistently really good, and so I've just been using them for years now. And here I will
So you upload like top layer data, stencil data, and then they will send
yeah.
you
So
stencil.
this is their site. It's not super pretty, but it's pretty cheap. I mean, it's like $10 for a stainless steel stencil.
Mm-hmm.
Yeah, and you upload the Gerber files that you want to upload in it, and they'll laser cut it and send it to you.
Mm-hmm.
So you know, if I'm doing a two layer assembly, I'll upload the top paste and the bottom paste and like the keep out layer or the tool routing layer or whatever. If I'm only doing one side, it's just, you know, whatever paste layer I need, and that's it. And then they send it over. So typically, what I'll do is when I order the boards from PCBWay, the same time I will place an order with Osh Stencil for the stencil, and I will order all of my parts from DigiKey or Mouser or whoever I'm using, and that way they all kind of show up at the same time, like in the middle of next week, whatever it may be.
This is exactly what can, for example, save time and money if you can
Yeah,
build it in one place, because you don't have to pay shipping from 3 different
yeah,
sources and you don't have to handle it.
yeah.
Okay, so you have the stencil, you receive the board. What you are going to do now?
So I have the stencil, I have the boards, I have the parts. This is the tedious part, right? So now the next step is typically take the board, put it down, I put the stencil on top, and I scrape solder paste across, right? So I guess the tricky part for the wand board though was it's so small, and they weren't panelized, right? I was just getting the bare boards like this, and so if you look, there's not really a good place to tape this down, right? Like every square millimeter is taken up by some component. So what I ended up doing is I grabbed some double-sided tape, and I put some double-sided tape on the back, and then I I taped that to my table, and then I could kind of squeegee the paste over it and place everything. And then, so then the next step is after it's got paste on it, I go and I take some tweezers and one by one, I put every part down and, make sure it's all roughly in the right spot. One of the nice things about solder paste and reflowing is as long as you're close to being in the right spot, when the solder paste heats up and reflows and turns into molten liquid solder, the surface tension of that solder paste of that molten solder kind of aligns all the parts. It pulls them to the right spot. So I have to be close, but I don't have to be 100% perfect exact, which is nice.
What solder do you use? Because there are like many. Do you have a favorite?
I don't have I don't
You
have
just buy
I don't
cheapest one,
I don't
or
have one on. I'd have to go look at it. I can send you a link later, but I'm sure I just went to DigiKey and I was like, oh, lead-free solder paste.
okay.
And whatever one was, they had some in stock and it was relatively cheap. I was like, that's the one.
Okay. And I've seen you have very nice, the device, the
The little
soldering
oven.
machine.
Yeah, the little oven. The little oven is probably one of the best pieces of equipment that I
Which one
bought.
it is?
It's the
Uh,
T962 or something like that. It's a pretty common one.
can you find it on internet?
I think it's the T962. Yeah, T962 reflow oven. Let's see. You can get it on Amazon. Look at that. That's exciting. Yeah, this is the one.
100,
So,
650.
oh no,
Okay.
that's not what I paid for it though. Hold on. We can. I think I paid $150 for it. Let's see. Look at AliExpress. Even that's too expensive. Here. This is probably more what I did. So
Are there
140.
differences? Or okay, size is maybe difference.
It might be size. The reality is, I don't think so. I think it's just a bunch of different resellers that are selling the same item for different prices. I think I probably paid like $175 for mine.
That's cheap.
And yeah, it really was not that expensive, all things considered. And I've had it for 3 years, 4 years, and it's baked hundreds of PCBs over the years. But yeah, I mean, it's great. I mean, and it has the option to, let's see if I can find a picture for it. I'll go back to that Amazon one so we can look at a better picture. But you can select from a whole bunch of different reflow profiles.
Mm-hmm.
It has a whole bunch of preset ones, or you can make a custom one. So if you want it to go up to this temperature by this minute, up to this temperature by, for if you want to do a soak and then you want to do a full bake and then, you can adjust it. It's every, I don't know, 2 or 3 seconds is granular. So you can adjust everything and it works great. The one downside to it is it's not a perfectly even heat distribution inside. So there are kind of like some sweet spots, like if I put a board here, I know it'll reflow. If I put a board over here, some of it may reflow. It's not consistent all the way through, but it's just, it's one of those things that you kind of pick up.
Okay. Let's continue with one.
All right. So I'm going to close that for now and the side panel just to make this a little bit bigger. So this is the wand as a whole. It's made up of 4 parts plus this leather wrap around the middle. And I will turn off the leather so we can kind of look at it. And I'll turn off all of those guys. So the 4 wooden parts. We'll start from the beginning. So first is this bottom piece, right? So you can see this is the cutout where the PCB sits, right? In this area. This is where the vibration motor slots into. And then this is kind of the well where the battery sits. I'm going to turn this and you can probably see there, one side of the wand is actually flat. You see this flat side right here? I don't know, let me see if I can do it from.
I can see it. Yeah.
There's so one side is curved, one side is flat. And the one thing that we haven't really talked about is how the battery and how the charging pads actually connect to the circuit. So I'll show you that in a sec. But this flat right here is for the charging pads that we'll talk about. So here's the bottom, right? And here, this is the battery, so you can kind of see where it fits, right? Let's see if I can find a better angle to show you. So battery, bottom part, and then if we include the wand PCB, right, you can kind of see now where it all fits relative to the battery, where it fits relative to the wand part. This whole thing is then covered by a top piece, top wooden piece. And inside this piece, it looks very similar to the bottom where it kind of has that scoop, that cutout for the battery, and it has another kind of scoop cutout for above the PCB for kind of taller components. And so this is actually, in reality, this is everything you need to make it work. The other 2 parts they're purely just aesthetic, right? They're just to look good. So here we have this little like end piece, this little cap, and here I'll turn off the top so you can kind of see. So this little end cap piece, highlight him. He fits in, kind of press fit, and then I added some wood glue just to keep it in place. And then the same is true for the top part, right? So again, kind of this big long piece, it just press fits in plus some glue just to keep it in place. With the top, right? So now here. So this is what it looks like, right? When all the wooden pieces are put together. Remember when we talked about it though, I want to make sure that it looks like it's one constant piece of wood, right? So ideally, I don't want to know that this middle piece, the part that I'm holding, is made of 2 different parts. I don't want to know that there's these metal charging contact things that are going to come out in a sec. I don't want to see that there's a split in the wood grain or anything like that. So to hide all of that, I thought it'd be kind of cool if I just added like a leather wrap around, and that way it just hides all of that, right? And I feel like not only does it hide it, but the aesthetic of it kind of fits.
It looks better, yeah.
Yeah, it looks like a magic wand, right? It looks like it was like actually meant to be that way. So I'm going to hide this leather again, and I want to talk really quick. Oops. hide that leather again, and I want to talk really quick about the charging and the battery context, because I think it's a little bit different than what I normally do, and I think it's kind of interesting. It's a little bit unique. So remember, I talked about those castellated pads, and those castellated pads, what they're there for is I bought some spring steel, like the same stuff that you would use to make a battery pack of 18650s or whatever it would, like that you would normally spot weld to the batteries. I bought like a coil of that stuff, and I thought, well, maybe I can just like solder that into one of those castellated pads. So right, steel castellated pad, it just comes in here, and then I apply, I fill in that gap with some solder, and then I could run that steel out along the edge of the wand, and I could make some charging pads with it. So let's see. So here, what you see is, I'll take off this top piece.
Nice.
So now what happens is there are these two pieces that run out from the board like that. And then at the very end, this is it. At the very end of the metal bands, or the very end of these metal pieces, there are these metal circles that wrap around the inside, or that wrap around the wood, right? So now it looks like this, right? And with the leather, it looks like this.
Oh, so you can have a holder, you put it there, and
exactly. So that's how you charge it, right? This top one is the 5-volt. This bottom one is the ground. Or sorry, no, it's the other way around. This top one is the ground. This bottom one is the 5-volt. And I actually made that choice of which one was where intentionally, because the way that the charger, which I haven't designed yet, but don't tell anyone, the way that the charger is going to work is I want it to look like almost like it's like a rock or like a stone or something that you just find in a forest, And I want the wand to just like rest on it, like you're just like leaving it on a rock, or something. And so what I thought I would do is the bottom one, if the bottom one is 5-volt, there's no way you can accidentally reverse the polarity, right? If the bottom one is where the wand sits, you can't accidentally connect ground to this bottom one because the tip of the wand would get in the way. So by putting them in this orientation, right, the bottom one being 5-volt, the top one being ground, you can never accidentally flip the orientation. So continuing on, right? So we have the charging bands, right? And I thought to myself, well, if I'm doing the charging bands like that, maybe I could do something similar for the battery, because a big connector for the battery, it would take up too much space. It would make this board, I would either, if I had a JST PH connector or something on here, it's too tall. Or if I bought a battery holder, to fit this battery into, I'd have to increase. I'd have to increase the diameter of the wand by another 2 or 3 millimeters. So it's too much space. So instead, I did the same thing I did with the outside coils here. Let's see if I can rotate it in a little bit more so you can see it. So there's one piece that kind of comes from the top of the contact, like that, kind of folds over itself into that castellated pad. And then there's another one that wraps around from the bottom, and it goes to the other castellated pad.
Very nice. So what exactly is this part? This
metal?
Yeah, the metal, yeah.
All right, I'm going to duck out of the camera.
We find it in DigiKey, or where did you buy it?
I think I just bought it on Amazon.
Because this is interesting, actually.
Yeah, it's something like this. Right?
Ah, okay.
So this is how it comes. It just comes like as a big coil of the stuff. It's really thin, so it's very, very easy to bend, right? It's very, very malleable, and you can just cut it with some scissors, right?
But it's still flexible, so you can bend it, but it's still also flexible.
Yeah, and so what's actually not shown in this CAD is it's actually so flexible that these kind of bends that I have that I had planned for, it's so malleable that I had planned for these bends, but they wouldn't hold, right? Because it would squish. So what I ended up doing instead is I had some neoprene foam. So I put a little bit of neoprene
Okay.
foam on both sides, and that allows the battery to compress the foam, but so the battery stays in place with the contacts pressed in, but it's not so tight that I'm worried about puncturing the battery, or if the battery swells or something during charging, it's not going to damage the cell. It's the foam is compliant enough that you can still
Yeah, I
move it
understand. Yeah,
around a little bit.
good idea.
Yeah,
How do you update firmware?
so once it's actually in the wand, I don't. The one that is currently built up, there's no way I'm doing anything with it ever again.
So you have to write bootloader or something first.
Yeah, if I wanted to, there again, the Dialog SDK actually allows, or they have some good examples for over-the-air updates. I didn't incorporate it in mine because I wasn't thinking that far into it. But it is something that I could do in the future if that's something that I needed to do.
So you basically glue everything together, and there is no way to access the board after
Yeah.
it's built.
And here, I actually have it right here, so I can just show you guys. I can show you. So this is what it looks like once it's all done, right? And you can actually see when I was making it, I accidentally bumped the CNC accidentally bumped up against this one piece after it cut it out. There's this nice little notch in the bottom, but this is what it looks like, right? And you can see these are the charging pads, right? And the leather wrap with everything. So this is it. I mean, everything is glued up, and the wand or the battery and the board are all in here. And it's like it's ready to go and do its thing.
Okay.
But yeah, so
you created this.
So I created this, right? And once all this is done, unlike in 3D printing, I can't just upload the file to a slicer program like Cura or something, right? For a CNC machine, it's kind of like, I don't know how familiar your subscribers are with these kind of machines, but a CNC machine is like the inverse of a 3D printer, right? So instead of building something up layer by layer by layer of plastic, you would put in a block of wood or a block of metal or something, and it's going to cut away at that material layer by layer by layer by layer until all that's left is what you wanted originally. So it's like instead of like, well, you get it, right? Instead of building up, it cuts away.
Yeah.
But unlike with 3D printing, you actually have to tell the machine where to go to cut away at all this stuff. And that process is called CAM, C-A-M, or Computer Aided Machining, I think is what it stands for. So there's CAD, which is Computer Aided Design, and that's the 3D modeling and stuff. And then there's CAM, Computer Aided Machining, and that's telling the machine actually where to go physically to cut away stuff. And so say I wanted to actually make all this, right? The next step is to actually design the CAM for that. And so I'll pull that up. And again, if I'm going on too long or if I'm ranting stuff, just cut it.
No. This is interesting. I don't know how this is done.
Okay, cool. So I will show you. So when you are going to design something or when you're going to do the CAM process, the first thing you do is you bring in the files that you want to bring in, right? So in this case, I was going to cut the top and the bottom piece of that inner wand part together. Mm-hmm. So I put them next to each other in the 3D design file, right? Then I go into this manufacturing tab of Fusion 360, but other programs like SolidWorks and others have this ability as well. I go in here, and the first thing I have to do is I have to define for the computer, for the machine, what the size of the stock is. So if there's a piece of wood in there, it needs to know how tall is that wood, how wide is that wood, how long is that wood, so that when it's cutting things, it doesn't accidentally cut outside of the bounds of your material, right? So the first thing I do is I go in here and I'll pull it up very quickly, but you can basically see I said, okay, it's 8 inches long, it's this wide, and it's this tall, right? And these are I have a physical piece of wood in my shop, and I measure it with calipers, right, to get as close to exact as I can. Once I do that, then the next process is figuring out how to actually cut away at this material. So the way that this is going to work is, again, unlike 3D printing, because I'm not just building something up from nothing, I'm cutting away. For this particular type of thing, I actually have to cut it on 2 sides. So I have to actually create 2 different versions of this CAM file. I have to do a bottom side machining, and then I have to flip it over and do a top side machining. And I have to be very careful when I'm doing it to align the stock so that when I flip it over, it doesn't accidentally cut in the wrong spot, right? So the first thing that's going to happen for this, and let's see if I can, I'm going to move this ever so slightly. So I can actually simulate it. So what I'll do is I'm going to talk through really quick the different steps, and then I'll show you what the simulation looks like so you can see what it was supposed to do. So the first thing that I want to do is I want to make sure that the top of the wood is perfectly flat, right? I don't want there to be any little bumps along the way, so that when it starts cutting, it's cutting a surface that it knows is exactly this height, right? And in fact, I even cut out a tiny bit extra just to make sure I know that the top of that is perfectly flat. So that first process is called a facing operation. So basically what it's going to do is the router bit that is just going to come across, it's just going to work its way back and forth and back and forth across the surface like this. Okay. So after it does that, the next step is a pocketing operation. So now what it's going to do is it's literally going to go in and it's going to calculate where all of these little pockets are. And it's, again, going to cut out step by step all these little sections along the way so that you can see, let's see if I can simulate both of those at the same time. So we're going to skip through the facing operation that we just showed. And then the next step is this pocketing operation. So it's going to go through layer by layer, cut away all little chunks of wood that it needs to cut away. The next step is what's called like a finishing operation. And that is, it's going to go through, and for this, I should take a step back. For the pocketing operation, when it's cutting stuff out, it's doing it at a really rough resolution. So when it's cutting stuff out, it may actually, you may be able to see steps on what would be curves normally and things like that. And the idea is to just remove a lot of material so that when you do this finishing operation, which I'm going to show next, this finishing operation is going to go through much slower, and it's going to cut away all that extra material to just make sure that you're actually getting those nice curves. Right?
You still use different, or you still use the same tool, same bit?
So
or you can change it for something smaller? Or?
Yeah. So the first 2 operations are the same bit, right? The facing and the pocketing are both going to be the same operation, or the same tool. The last operation is going to be a different tool, or it's a different bit. And I'm turning off this sketch. And instead of being a flat bottom, it's a curved bottom. And so the idea is,
so you don't see the
when
steps.
I go through here, it'll be a nice curvature that follows the curvature of the tool. So here, if I kind of move around, you can kind of see. So now where that battery goes, instead of just having steps, it's like it's actually a nice kind of little cylinder inside, right? So I do that for both parts. Once I do that for both parts, the next step is to literally take this part out, flip it over in the machine, and then do the other side.
But
now the other side,
how do you actually do it? Is there like a button which you say like generate this path, or you have to somehow draw the path? Or
oh yeah, so okay, so this facing operation, So Fusion 360, which is this program that I'm using currently, it will generate what it assumes to be the best tool path for the parameters that you give it. So in this case, when I do this facing operation, I don't know if you can see the stuff on the right hand side.
I can see.
Right, I'm showing I'm setting the spindle speed, so how fast that router bit is moving, how fast I'm going to allow it to cut along the way. Then I'm showing it what the bounds of the area that I want it to cut are. So that's what that yellow square is. Then I'm showing it how high, or sorry, then I'm showing it how far down it can cut. So this light blue line is the surface, or sorry, is just above the surface material. So that's telling it this is how high I want you to pull the bit away when you're moving, so you don't accidentally bump into stuff, right? And these retract and clearance heights are similar. They're different levels of how far I need to pull the thing away. The dark blue line is how far down I'm going to cut. So from the light blue line to the dark blue line, that's how deep I'm going to cut, right? Then, in addition to all that, I need to show what the maximum depth per pass I'm going to allow. So this is kind of like the layer height in 3D printing. And this is just this is dependent on the material. So the harder the material, the less material you can remove with the same spindle speed and everything. So for this wood, I was using, what is this, 1/8 of an inch or something like that, or 1/16 of an inch. And then there are a couple other, additional parameters, like how the tool comes in, whether it spirals down like a drill bit or it comes in from the side.
I didn't know you have to specify all this.
You gotta specify all that, and depending on the operation. So like the facing operation is different than like the pocketing operation. Right? So in the pocketing operation, I actually specified that I want like a helix ramp in for the cutting, and I'm specifying, which side of the tool I want to actually do the cutting. So let's see if I can point that out really quick. So when you're machining things, the spindle, like the router bit, is spinning in a certain direction. And if you think about it, so say the spindle bit is spinning like this, say it's, I guess this would be counterclockwise for you. So say it's moving counterclockwise. If I were to move counterclockwise around the material like this, right? What's happening is every time it moves a little bit, the tooth of the spindle is grabbing a big chunk of material every time it bites, or every time it hits, right? If I move this way. If I go the other way and the spindle is still moving counterclockwise, it's now grabbing a small amount of material and then it gets bigger. And I don't know if I'm explaining this properly, but there are two kind of methodologies for the direction that your spindle is going to go. It's either conventional or climb are the two different ways. But it either means no matter what direction my spindle is spinning, so my spindle is spinning counterclockwise, how do I want the tool to move? So I can either go clockwise or counterclockwise, with the spindle moving, or I can go the other way, right? And depending on that, certain materials do better with conventional, certain materials do better with climb. And it depends on how much material you're trying to remove at once. If you're trying to avoid any sort of like heat dissipation, so if you're doing like aluminum, you typically want to do, I think, climb rather than conventional, so that the bulk of the heat is then dissipated into the small chunks of metal that you're flicking away, rather than into your stock material. So there are a whole bunch of different parameters, right? A whole bunch of different things that you have to design.
How do you do it? Then you Google before you start making?
Yeah, when I first got the CNC machine, it was a lot of Googling, a lot of asking people that knew what they were doing. And now it's just like anything, just like anything else with circuit design, right? Like there are certain conventions that you now know that you follow, that you just reuse over and over. Like, I know that a power trace has to be bigger, or things like that. And it's kind of similar for this.
So, but you don't have to specify exactly where it should go. The
Yep,
path is generated based on the 3D model which you have here. You
that's
just
correct.
specify some kind of properties how the tool is going to move.
Yes. Sometimes though it gets a little bit trickier because the toolpath that it generates is not good. Like sometimes it wants to cut right through the right through your file, or sometimes it's just it's a very inefficient path, or it wants to cut away too much material to. So part of the art is kind of figuring out kind of I guess the art is kind of figuring out the best way to generate those files, right? Um, so yeah, so right, so like we did one, and I won't do this for the tip and the butt of the wand because it's the same process. But
Okay.
so you do one side, right, which is we did the facing, the pocketing, and then we did this kind of finishing parallel path. Then if you look, you can see this is where my origin is, right? The Z is pointing straight up, the X is pointing one way, the Y is pointing one way. If I go to the other side of the operation, I've now flipped my origin point. So now my Z is pointing a different direction, my X is pointing the same direction, and my Y is pointing the opposite, right? So you think about it, you have to make sure that you mirror it appropriately so that it cuts out the same piece. So now for this side, right? This side's a much easier side to think about because you're just trying to make this convex shape, this cylinder shape. So for this one, the first thing again, we're going to face everything down just so that we can get rid of all this extra material that we don't need. Then we're going to do another pocketing, kind of like what we did before, but we're just going to cut out around these cylinders, kind of coarse, not very high resolution. Then we're going to go through and do that finishing pass to make it look really nice and smooth. And then we're going to go the last thing we're going to do is then finally cut it all out so it kind of falls out of the block of wood. So again, we'll simulate it just to show you, right? So it's going to do this facing operation. It's going to go through a couple of layers of this. I'm just going to skip ahead. Then it's going to do this pocketing operation. You can kind of see now where those steps are. And then finally, it's going to go through that finishing pass and give it a nice round edge. And then once it finishes that nice round edge, it's going to go through and finally cut the piece out.
How many times did you have to do it? Was it
On the
like first
machine,
time?
on the machine, it was the first time, but I did a whole bunch of simulations before it was ready to go. I luckily, again, I've now done enough work on the CNC machine that I kind of know what to expect. And if I can make it work in the simulation, it typically does exactly what I'm expecting on the machine. So that's the cam. That's how that works, right? So I have to do that. I then do that for not just for these pieces, but I also did it for these pieces, right? For the
Mm-hmm.
top and the bottom, right? And I won't walk you through all the steps, but I'll just show you quickly, the simulation of it. I'll just move this over a second. So here you can see kind of the rough pass, right? You can see that kind of steps. Then I'm going to go through and I'm going to go do that kind of finishing pass all the way. Give it a second to load. So you can kind of see now it's nice and smooth all the way through. Then it assumes I'm flipping it over. So I'll go ahead and run it and then I'll flip it over so you can see. But here you can see there's still a little bit of material left intentionally, right? Like this green right here.
Yeah.
Intentionally leave that little bit of material there so that it stays in place while I'm running this operation, right? So now I did another rough pass. I do another finishing pass where I smooth it all away. And then finally, once all that's done, then I cut it free.
This is interesting because when I was starting with 3D printing, I was like, first time I saw 3D printer, I was like, oh, I can print anything. And then I was like, not anything. There is this limitation, and then you
Yeah.
have to think, oh, okay, I have to split it into multiple parts and maybe glue them together.
yeah, so it's very similar for this, right? Like I have to start thinking about all these different parts. And actually, hold on one sec. I have two additional parts, and I started making another one for my fiance, so we have two of them. But here's like the little butt part, and here's like the wand part, right? And so those go, I guess, compare if we're looking at the screen below, right? They go like this on that cylinder piece, but you can kind of see this is what they look like when they come fresh out of the machine. Um, so that's it. That is the whole thing. I don't. I'm trying to think if there are any other steps that I'm forgetting to tell you about now, but I think that's everything. I think that's how you make a magic wand.
Nice. We can have a
Yeah.
quick look on the plaque
Yeah.
circuit, but just very quickly because it's
Yeah. I know it's crazy late for you, and I'm sorry to keep you up so late.
no, it's okay. Don't worry.
Do you want to look at the board? Do you want to look at the 3D files? What do you want to look at?
Board. I would like to see the board. What is on the board? Because there is, you know, higher voltage than
Yeah,
1.5 or
it's
3.3 volt.
definitely a little bit scarier. So normally for my projects, for all my projects, I like to make them fully open source, and I like to let anyone that wants to make them can make them. I'm a little bit more hesitant about the plugs because of the fact that they are high
Safety.
voltage and they deal with mains. I'm happy to talk about them in the video, but I don't know that I'm going to release the files the same way that I do for other projects. If someone has the know-how to recreate these files from the video, I'm hoping that they also have the know-how to they also have the know-how of what is going to happen if they plug stuff into the mains. But I want to present that as a warning. If you don't know what you're doing, don't do anything with wall electricity. It's scary and very dangerous. Now, with that being said, let's go do stuff with wall electricity. Okay, so for this, it's probably very similar. It's like a stripped down version of what you saw in the wand. Again, talking about it as if it's like a body. There's the microcontroller, which is like the brain, the actuators, which in this case is just the relay, and then there's some power stuff. There are no sensors on this board because there's nothing to sense.
Yeah.
I don't remember where I may have put the button. I don't remember where I put the button, but we'll look. Where did I put the button? Oh, it's right here. Okay. So I just included the button on the microcontroller page because it wasn't enough to deserve its own page. But this is, again, very, very similar to what we just saw with the wand. Same DA 14531 part. Most of this is unchanged. The only major difference is there's no longer I squared C because there's nothing running on the I squared C bus. What was the motor, the vibration motor IO, is now just this relay enable pin. And we have this button running on a different IO into the microcontroller. Otherwise, it's the same thing, right? Memory stayed the same, the JTAG stayed the same, all that stuff stayed the same. On the actuator front, this is a little bit different, right? So now what we have is the relay enable that comes from the microcontroller that drives this FET right here. The FET is then going to pull this low, which is going to energize the coil in that relay. And at the same time it's doing that, it's also allowing some current to flow through this one blue LED, just so you know that something's on or off, right? And then the output of this relay, it's a normally open relay, so in theory, if something fails, it'll disconnect everything, in theory. But again, when you're designing for kind of these scarier voltages and stuff, you want to think about how things are going to fail, and if they do fail, how can you prevent them from
this is nice actually
being catastrophic, right?
Yeah.
So I assume you probably talked about like net classes and stuff in some of your videos, but I'm just making sure to label all of my high voltage, high current nets as kind of this AC voltage, so that when it comes time to do the layout, I can make special rules for them to allow for creepage and clearance constraints and things like that. So here we go. Here's the relay. And then from the relay, it then it energizes the output AC plug. So the neutral line is staying connected. It's just the hot line that is getting toggled on and off. And then earth ground is staying earth ground. So the neutral and the earth ground are connected all the way through. It's only the live or the hot that is being energized or not in this scenario. All right, moving on to the power. So the power stuff, it's pretty straightforward. You've probably seen some of these AC to DC power blocks. You've never seen these before?
No.
Oh man, are you in for a treat? All right, HLK PM01. They're the best. It's literally all it is. It's a fully enclosed, potted AC to DC converter.
I've seen something similar, but not for 220 volts. This is nice.
Yeah.
Some people actually ask about this kind of circuit, so this can help some.
Yeah, these are great. I spent a lot of time thinking about whether or not I wanted to design my own AC to DC. And the end result was, not only was I going to spend more time doing it, but to get custom magnetics and things like that, it was more expensive than just buying something like this.
Mm-hmm.
These particular parts are made by this company called Highlink, which is this Chinese company that I don't know all that much about, to be completely honest with you. They've been around for years, and these blocks are in tons of hobby electronics. If I was going to make this into a real product, I probably would not use this particular block.
But something similar.
There are, so on DigiKey you can go and buy, I think Recom, it's AC DC. So there are companies that make this same thing. Let's see, they make the same thing. They're just more. You're essentially paying for some additional. You're paying some additional price for the peace of mind, right? So here, if I go with enclosed, so here you go, right? So Recom Power makes the same thing, right? Mm-hmm. For all intents and purposes, they're the same deal. Kui makes them, a couple others. The reason I picked this one was it was a little bit cheaper, but two, there are a ton of different versions of these Chinese knockoff versions of it. But this one in particular, there were a whole bunch of people that did some actual safety teardowns of them. And I felt after reading through all these teardowns and looking at the actual electronics inside, I felt more comfortable about actually using one of these. So there's a whole bunch of extensive data testing that's been done. And granted, these were not done by certified, safety, agencies. So they're not 100% accurate. These are crowdsourced data. This is crowdsourced data from other enthusiasts. But you can see it's fully potted. They follow proper creepage and clearance constraints, right? Looking at the right-hand side, you can see the slot that they have over there to allow for proper, clearance constraints. And then again, same thing here, right? You can see that they're using some custom magnetics. They have a varistor inside. There are a whole bunch of additional things built into these. Now that I've talked about that, I still don't 100% trust them, right? And I think you'd be a little bit crazy to 100% trust them. So in addition to one of these in line, I also have, I included some fuses in line just to make sure that if something goes wrong, we pop some fuses, we detach everything from the system. And this is that same buck converter that we saw on the wand. And that is the entirety of this schematic, right? There's not much else. We can hop over to the layout, and I can show you. It's also pretty straightforward. You'll notice there is a large lack of copper on the left hand side, and that's to account for the fact that I don't want any nets on these high AC lines to be anywhere near each other. Right? I want to make sure that they maintain proper clearance, so that there isn't any sort of arcing or anything, across those gaps. So this is everything. Everything on the left hand side is the AC. Everything on the right hand side is the DC. And I will pop into 3D mode. So the way this is going to work now is there are two parts. There's this bottom plug part that actually plugs into the wall, and this is made by Heyco, Heyco, and I'll pull it up really quick. I think maybe it's this one. No, it's surprisingly very hard to find someone or a company that makes the blades that go into a wall outlet, right? And for some reason, no one makes those, or like no one makes them that are readily available, because often they're just custom stamped metal pieces that you're making for your specific design. These guys, they do make them that you can buy in bulk. So this bottom assembly, right, you can see with the two blades and the earth ground pin for the US version, right, comes in this, I think this is PVC plastic, right here. And then the top part, I can't remember who makes this piece, but it's like an IDC connector, right? So you run wire out from it, and then I have the wire soldered directly into the board. This all then sits inside the housing, right? Let's see if I can get a better angle so you can see some of the lighting better. Okay, yeah. So you can see, so this top piece, this top lip sits outside of the housing, and then this piece presses up on the inside so it doesn't move, right? And then the bottom, this board, is then epoxied to the bottom of the housing.
So did you 3D print the housing, or?
No. And that was a whole nother, that was something else to learn this time around. I learned all about flammability ratings. So when you're designing electronics for wall outlets and things like that, you have to be careful, right? Like if for some reason something goes wrong inside and you start a fire on your circuit board, whatever is covering it, the casework, you need to make sure that if there's a fire inside, it's not going to ignite and make everything way worse, right? So there's a UL rating, UL 94, that talks about specifically about what materials, what the flammability of different materials are. And I want to make sure I get this correct, but I think it's V0 or V2. There's some rating of some material that is essentially, if something catches fire, it will put itself out within 10 seconds and it won't drip, right? Molten plastic. And there are a whole bunch of different materials that kind of fit the bill. For this particular application, PVC plastic, like the same stuff that you get for like your tubing for plumbing and stuff. That type of plastic has a very good flammability rating. So I bought some blocks of PVC plastic and I machined away the housing. So same thing like with the wand, I used the CNC to cut the housing blocks. And I'll show that in the video when I talk about the smart plugs. But yeah, so then for the plugs, there are now two parts. It's like a clamshell that fit together with the board inside in between. And here for this one, I actually did do a test cut to make sure that everything would fit. So I have this is MDF, just like wood or like wood composite type stuff. But these are the two parts of the housing. You can see this is where like the plug comes out of. This is where the big plug goes, right? This is the spot for the LED, and then this is for the button, right?
Mm-hmm.
So these two then just fit together. I don't know, I'll probably get it to work, but these two fit together, and that's the whole thing. Yeah, that's how that worked. That was the smart plug.
That's what we will see
Yeah.
in the next video.
That's what you'll see in the next video. That's right. Yeah, I'm trying to think of a good way to present the smart plug information. You know, a magic wand is very fun, right? It's like very easy to like, oh, I made a magic wand. Look, it does things. I feel like a smart plug is not a very exciting topic. So I'm thinking through a couple different ways to kind of present that information and try and make it a little bit more interesting. I think my plan long term for the channel is I would like to make a kind of more fun, fluffy video like what I did with the wand for every project. And then I'd like to do a second video that's a more technical deep dive, kind of like what we're doing right now for all the projects, so that people that aren't interested in the technical stuff don't have to listen to it, and those that are interested in it can actually learn something from it. So that's the plan. We'll see how it plays out. We'll see if the channel can get enough attention and grow enough. You know, I'd love to do more stuff with it. So we'll see how it goes.
And that's everything for today's video. If you like, you can go and see Sam's YouTube channel. You can watch his video about this magic wand. And I would like to thank you very much to Sam for finding time to create this video. And I found it very interesting, especially about this CNC. I had no idea how this is done, so it was something new also for me. If you have any questions, what you would like to ask, or if you would like to just provide some feedback, how did you like this video? Don't forget to leave your comments. You know, say if the video was too short or maybe too long. You know, this kind of standard comments. If you like this video, don't forget press like button. If you would like to see my future videos, don't forget to subscribe. By the way, I would like to thank you so much for 50,000 subscribers, which we reached yesterday. And that's everything from me. I would like to thank you very much for watching, and see you next time. Bye.